quadratically constrained optimization problems. By now, you probably know what this all means. You still have quadratic objective function, a quadratic set of constraints. Again, if Q naught and all the constraints are quadratic, but the QK matrix is positive semi-definite, then the problem is convex. And otherwise, this is a repetition of what we saw before. There's usually the introduction of a new auxiliary variable yij that's equal to xi times xj and yii that's equal to xi squared. This is already something we know from the last couple of hours. The reformulation step, again, we saw it before. We get a new matrix of variables y, and this introductory part you already know. The fundamentally bad constraints are the ones that impose yij equals xi times xj. So here's the crucial point here. Now we're trying to use another technology. And we are still starting from the basic constraint y equals x times x transposed, which can be rewritten trivially as the difference of two matrices, capital Y minus x times x transpose equal to 0. Now, this nonlinear constraint, nonlinear, non-convex equality constraint, implies, that is, it's basically decomposable in two sides. Y minus x transpose is positive semi-definite because it's a difference of two matrices that is supposed to be 0. And if a matrix is all 0, then it's obviously positive semi-definite. So this is a perfectly fine constraint. And the best part is that this is a convex constraint. So now you could relax your original problem, this problem, instead of having y equals x times x transpose, which is non-convex, you replace that constraint with a semi-definiteness constraint, the constraint that imposes y minus x times x transpose, positive semi-definite. There's an even better way to formulate it, which is more compact and it's actually stronger. It's written by getting help from the Schur complement. So this is true if and only if this matrix, which I construct with a 1 in the upper left corner, the row vector x transposed in the rest of the first row, x, the column vector x in the rest of the first column, and then the y matrix in the rest of the matrix. This matrix, which is an n by n plus 1 by n plus 1 matrix, needs to be positive semi-definite, and this is going to be equivalent to this. But for semi-definite optimization solvers, this is going to be an ideal way of inputting such a constraint. We could also say, well, why don't we write the opposite constraint? That is, if y minus x transpose equal to 0, then obviously x transpose minus y is also a positive semi-definite matrix. The problem is this is a non-convex constraint. And there's no way we can reformulate. There's no way we can just introduce it because we would get back our non-convexity. If you think about it, this is a constraint saying that a given matrix is positive semi-definite. What is the set? How does the set of all n by n positive semi-definite matrices look? What type of set is it? It's a cone. A cone of positive semi-definite matrices is such that, well, if you stay inside the cone, then you satisfy this constraint, which means that we are taking the matrices for which this conic constraint is enforced. So now this is your relaxation, semi-definite optimization based. You have linear objective function, linear constraints, and now you have a positive semi-definite constraint over x and y. And you obviously keep the linear constraints ax lesser or equal than y. This is obviously, as I said, a convex problem. I didn't even add any integer or binary variables simply because we are already facing some problem with the non-convexity of the objective function and the constraints. But the nice thing is this is actually a a convex problem. And if you added integer or binary variables to this problem, then you would get also a convex mean law. It's a bit tricky because it would be a mixed integer problem with STP constraints. And as far as I understand, there is no solver out there that can solve problems with semi-definite relaxation and also binary and integer variables. Is anybody familiar with the max cut problem and its approximation result? Raise your hand. Okay. So if none of you know this result, this is a perfect example of how using a completely alien technology like semi-definite optimization helps in solving a problem that is purely discrete, purely combinatorial. So maybe you never heard of the max cut problem, but if you have an undirected graph G, where V is a set of nodes and E is a set of edges, I assume that obviously everybody knows what a graph is here. I hope it's a good assumption. A cut in that graph is defined by a subset of all the nodes, and it's basically just a set of edges ij such that I is on one side of the cut and j is on the other side of the cut. You just split the cut into two, the nodes that are on the left and the nodes that are on the right. Every edge that is the bridges between the nodes on the left and the nodes on the right form a cut. The max cut problem asks you the following. Find S, find the subset of the nodes, so not empty, and a strict subset of the set of nodes, such that the cut defined over S has maximum cardinality. If you take a graph, you want to find the cut that gives you as many edges as possible. This is a combinatorial problem. It will be easy to formulate it as a mixed integer linear optimization problem. It seems like a perfect application. We simply need to define variables xi that are binary to say whether a given node I is in the set S or not. And because we need to count it in the objective function, we need to define another set of variables yij that is also binary, and that tells me whether an edge is in the cut or not. And we want, I don't write it there, but what I want is yij is equal to 1 if and only if xi is equal to 0 or xj and xj is equal to 1, or xi is equal to 1 and xj is equal to 0. And that's precisely what we want to maximize. We want to maximize the number of edges across the cut, and we want to maximize the sum over yij. Yij is only equal to 1 if I is not in S, but j is in S, or vice versa. I is in the set S, and j is not in the set S. This is an exercise in modeling. I hope it's clear with everyone. How do we model this with linear constraints? What I propose, and it may not be the best, way to do this, is the following. You only need two constraints. You need yij to be less than or equal to xi plus xj, and at the same time, it's also less than or equal to 2 minus the same summation. Why? Because if xi is equal to 0 and xj is equal to 1, then this right-hand side is going to be, let's say 0 and 1, so it's going to be 1. And 2 minus 1 is going to be 1. So all is good. Yij is less or equal than 1 on this side and 1 on this side. If both xi and xj are equal to 0, then this constraint will be the most restricting, so yij will be forced to be 0. If both xi and xj are equal to 1, then 2 minus 1 plus 1 will force yij to be equal to 0. Do you agree with this model? Looks like it works. I don't need any other constraint. I don't need any constraint on the form yij greater than or equal than something else. Why? Because I'm already maximizing them. So the solver will just see those constraints and say, I want to maximize the sum of yij, so I'll just push them up as much as possible, as long as I satisfy these constraints. What is the optimal solution of the continuous relaxation of this problem? So if you were Gurobi or Cplex and you were to solve this problem, you don't need to be Gurobi or Cplex to give me an optimal solution to the continuous relaxation to this problem. What is the optimal solution? So every xi is equal to 1/2. And yij, all the yij's would be equal to 1. So we get a very nice solution. Every edge of the graph is in the cut. Obviously, that's infeasible. That doesn't make any sense. And the worst part is that Cplex obviously will have other stuff to do with this problem. But in principle, if you had this relaxation, you would get all the variables. You will all get the yij variables equal to 1, and the xi and all the xi variables equal to 1/2. So you have plenty of choice for branching, and the problem is those variables xi are going to stay at 1/2 for a long time. Before you get an actually integer solution, it will take a long time. So this is a mixed integer linear optimization formulation for this problem. It's horrendous. I don't think Cplex will ever try find a solution even for smaller graphs. But maybe has Cplex is more than a branch and bound, so I'm pretty sure it can actually do better than I think. So the result, which some of you know here, by Guman and Williamson, says the following. No, forget about the mixed integer linear optimization formulation and formulate it as a nonlinear problem. So this time we want to maximize a sum of terms that are all equal to xi minus xj. And this time I'm simply saying that I'm actually not using binary variables, but just variables that have value equal to -1 or 1. You can understand that if xi is equal to j, so I and j are on the same side of the cut, then obviously this will be equal to 0. Doesn't have any contribution in the objective function. If these two guys are different because I is in S and J is not in S, then the difference will be 2 or -2. The square will be 4, so that means that I need to divide by 4 the objective function. This objective function will give me exactly what I need, so the number of edges in the cut. I don't need constraints. So this is a mixed integer unconstrained optimization problem where I obviously have constraints on the xi. They must be either -1 or 1. The continuous relaxation of this would be equivalent to the box quadratic optimization we saw half an hour ago, because you only need to reformulate it as xi between -1 and 1. So from this formulation, what we get is we just scribble on paper and we end up with pretty much this formula for the square of xi minus xj. So we end up with 2 minus 2 times xi times xj. And so an equivalent formulation is the maximum, again, the maximization of an objective function that's the summation over all the edges of 1 minus xi times xj. This is equivalent to the original formulation. And again, I don't need any other constraint. Okay, now I'm introducing constraints because I want to put in the I want to start using this semi-definite optimization relaxation. That's precisely what I do. I take these product terms xi times xj, and I replace them with a variable yij. So now I have this objective function, which is linear, it needs to be maximized. And I only need to say that y itself is positive semi-definite, and this is the most important thing, yii is defined by definition equal to xi times xi. Xi times xi, if xi is either -1 or 1, is always going to be 1. This is a crucial constraint. You can't just add the positive semi-definiteness constraint on y, because you obviously get a much better bound if you set yii equal to 1. The greatest, this is a very famous result, and And it mixes semi-definite optimization with a purely combinatorial problem to say that if you take this problem, you solve it to optimality. Again, this is a continuous problem now, continuous convex problem. What you get is an optimal solution that is at least 87% of the actual optimal solution of the original problem. 87% is a lot better than what you would get with the mixed integer linear optimization formulation we saw a couple of slides ago. So this was just to give you an example of how powerful semi-definite relaxations can be. Now, let's get back to the more continuous optimization problems and continuous non-convex problems. The original problem, as we wrote it, is, again, the minimization of a quadratic function subject to a bunch of quadratic constraints and possibly some linear constraints. The relaxation we get is by introducing extra y variables. Now the y variables should be already a mascot for this day because we saw them in every session since the morning. The relaxation has a linear objective function. The quadratic constraints have been changed into linear constraints because of the y variables. And now I simply need to impose constraints on x and y. And in general, I simply say that x, y belong to a set capital F. And then I keep with me, obviously, the linear constraints. F is dependent on the type of relaxation I choose. In the case of a semi-definite optimization relaxation, F is simply equal to the vectors x and y such that this matrix, the Schur complement, is positive semi-definite. In the McCormick relaxation instead, the set F is simply the set of x and y that this x should be, okay, I copied this from another slide and it should have been different. So this is not x3, this should be yij, this should be lj times xi. Let me wonder if no, it's gonna take me longer to write it on the laptop. So they should have been rewritten as yij, this is a last change minute as usual, greater than or equal to lj times xi plus li times xj minus li lj. Again, these are McCormick inequalities and they should be already in your head by now. Ujxi plus uixj minus uj. And then yij less or equal than ljxi plus uixj minus ljui. And finally, yij less or equal ujxi plus lixj minus ujli. So this is what was supposed to be written there. This is probably the last slide I have for this morning, and it shows the following. So if you actually do some experimentation with the same box QP that we tried in the other half hour with the paper with the Guboli paper by Gunluc, Linderoth, and Bonamy, they were trying to solve the same set of instances. This set of instances, I believe it has box QP, so box quadratic optimization problems with 30 variables, I think a density of 70%, and then just an index. For these, so these are not very large problems, but the McCormick relaxation, which has n squared, so 900 variables plus the original 930 variables, struggles quite a bit. And I think these are the results after solving those relaxations to optimality, both the McCormick relaxation and the semi-definite optimization relaxation. And what happens is the following. For these instances, they're all relatively small. They're only 30 variables, 30 by 30 matrix. The optimal value is known because it has been found before. These are actually formulated, this is important, as maximization problems. It doesn't matter if you have, it doesn't matter whether you formulate a problem as maximization or minimization if all you have is a non-convex quadratic. So, but they choose, and Stryker chose to model it as a maximization problem, which means that the dual bound is now going to be bigger than the actual optimal solution. So this is the optimal value for an instance of with 60% density and a matrix that is 30 by 30. The RLT, it's called here RLT, but it's basically just the McCormick constraints. The McCormick constraint gives you a bad upper bound, a dual bound of 1400 for an optimal value that is 700. Baron probably didn't work too well at the time, and it gives a slightly better bound. This one is not important. The semi-definite optimization relaxation gives you a bound that is much tighter, 768. And so the natural thing to do is, okay, so we have a nice relaxation with the semi-definite optimization, the semi-definiteness constraints. Let's try to pair the McCormick constraints with the semi-definite constraint. And what happens is that the bound gets even stronger. So you see, I've showed this pattern, I show this for the first row, but a similar pattern happens for all instances. Let's do an exercise. I mean, this is more of a linear algebra exercise, but it will show something about the actual constraints that we need to write when we write a semi-definite optimization relaxation. If you have the Schur complement written like that, for n equals 1, which means that the matrix itself is a 2 by 2, and for n equals 2, which means the matrix is a 3 by 3, what do we get as... So what does it mean to have a positive semi-definiteness constraint? Let me write the first case here, which is 1, x1, x1, y1, 1. This is trivial. If I want this to be positive semi-definite, what do I have to say? y11 greater or equal than 0. And then? Okay, y11 minus x1 squared greater or equal than 0. This is one of the convex constraints we saw before, right? X squared less or equal than y. This is obviously a convex constraint. Okay, that was trivial. Well, we need to also say that 1 is greater or equal than 0, but I won't waste chalk on it. This is 1. So for the case of n equals 2, we have x1, x2 here, and x1, x2, and then y11, y12, y21, y22, greater or equal than 0 if what happens? y11 greater or equal 0, y22 greater or equal 0. Oh, yes. Okay, yeah. y12 equals y21. I mean, this is not necessary. So this is not implied. Has nothing to do with the semi-definiteness. But if we want to reformulate with the auxiliary variables, then this constraint will be necessary. What else? We need all the 2 by 2 minors and the single 3 by 3 minor, right? So what we get is the first 2 by 2 minor is y11 minus x1 squared is greater or equal than 0. So same as over there. And then something similar happens with the other minus. So y22 minus x2 squared greater or equal than 0. There's 2 missing, right? So the 3 by 3, how do we write the 3 by 3? That's the trickiest. Let's write the 2 by 2 here. This is interesting. y11, y22 minus y12 times y21, which is y12 squared, is greater than or equal to 0. What constraint is this? It's a second order cone. For the 3 by 3 minor, we will get a third degree inequality. Oh, that's a bonus that has not much to do with Milno, but might also be interesting. Pretend you're a branch and bound solver and solve this mixed integer linear optimization problem. What is the, so at the root node, what is the optimal solution to the continuous relaxation? Look at the objective function and the coefficients. Y has a negative coefficient in the objective function, which we want to maximize. So what's the, okay, so the root node, what is the solution? Anybody at 1? So the coefficient 2 to the n minus I is decreasing from the first. Okay, so the first node has 1. If you use heuristics, the x1 will never be 1, right? Because it. Okay, x1 is equal to 1/2, and then 0, 0, etc., 0. Right? So I branch x1 lesser equal than 0, x1 greater equal than 1. What's this node? It's infeasible because of the constraint can't be satisfied. So what happens now? We have exactly the same problem in 1 dimension less. So now we'll have 0, 1/2, 0, 0, etc. And so on and so forth. x2 greater or equal than 1 is infeasible. I will get now x2 and x1 both equal to 0. And so on and so forth. I'm sorry? Here it doesn't increase exponentially, right? It's just a waste of time because you descend the branch and bound tree until depth equal to n, and then you realize finally that all the x variables have been set to 0, because if they get set to 1, the problem is infeasible, and all you are left with is y equals to 1, which gives you a feasible solution with objective function value -1. Okay, I think we can stop here. Are there questions? Slide? F is I just wanted to make it generic here so that then I could write a feasible set that's different for different relaxations. So F is simply a feasible set for x and y, which is defined as a semi-definite cone in one case and the McCormick in the other. So these matrices have been randomly generated. Not every element of the matrix has been randomly generated, but 60% of them have been set to be non-zero. The rest is 0. So yeah, 60% is a sparsity, yes.